All right, welcome back after Thanksgiving holiday. And today we are going to discuss about two things. Number one is homeworks, another one is the typical syllabus materials, air quality. So this week all will be air quality. But because I know that many of you have difficulty in the homework question 6, so I will discuss at least first half of the class how to set up those questions or answers. Um, Couple of announcement. I know that somebody asked question on exam. This is one of the things that I plan to grade exams, but I didn't finish the solution until this weekend. So TA didn't have my solution, so that's why they have not graded some of the questions that they are assigned to. So that's again it's my fault because I didn't do it in time. So you should be able to receive your grades, or at least by end of this week. And one thing we do is if you send me any materials, whether it's a homework, late homework, or anything, TA doesn't have access to those. So you might not see your grade there. So send me email if it is not there because I do update those grades. Um, but exams, the TA has access if you send me by email. But homework, you should look for all those. If your grades are somewhere less than or something is not graded, it's missing. Next 2 or 3 weeks is the time for you to, 2 weeks actually, next 2 weeks until the final week, end of final week, you should be able to send me emails for any, because you could check all that grades. That way we could rectify before we submit any grades. Um, so there is a questions on will the midterm solution posted on CCL? Yes, I'll post later today after verifying um, with the TA. Will you know by the pass and non-pass deadlines on Friday? I don't know about those things. So you have to check with because this is not something I control. So wherever the deadlines, you could be able to say yes or no. And again, as I said, nobody's failing this class. If you submit all your homeworks and exams, you are not failing the class. Failing means not receive any grade less than C. By default, by submitting everything, you are getting C. But obviously, that's not what my aim is. My aim is that you do well. So that's so. But after your midterm score is there, again we'll discuss. If you have done really poorly, and you wanted to do well, so we'll see. What's the how much grades you have remaining. Again, I would not worry too much because you still have finals, at least one more homework, and we'll check what else remaining. I think what they're asking is, will you know midterms grade by Friday so we know how we. Okay, I see. So if it's a Friday is the deadline, I'll make sure that you have your midterm grades before Friday. That's a good to know. So let me write a note. Midterm grade by Friday. One thing also, if you are particularly concerned, you could send me a message so that I can check your personally, so that I can immediately let you know without waiting for TH. But again, if it is like too many people, then obviously I'll take time. Okay, so that's about the final. Um, Again, office hour is Tuesday 2 p.m. I just put it there just because I know that you guys need help with the homework number 6. And there are many questions you guys ask on campus where I didn't really go through all of them. So that's why I wanted to have office hour, including today's half of the class, to dedicate this because this is important homework for final. So I want to make sure that you guys know about how to solve this. Um, Again, for air quality, I just uploaded the textbook chapters. You don't need to read the entire chapters. The only thing that matters is section 1, 3, 5, 11, and 12. Mostly the quantitative part is 11 and 12. So the questions that's long questions or things that you need to solve is question number 11 and 12, the section 11 and 12. 1, 3, 5, these are just reading about what is air quality. all the pollutions, all that stuff. So it's really not much there in terms of the quantitative aspect. So again, these are all uploaded. Today, again, my objective is to make sure that you are comfortable solving questions on homework number 6. That's my primary objective. And second thing, we'll just go over through the air pollution, very basic part. And next week, next class, we'll go details about how to use mass balance to solve even larger or the big problems like plume, how plume moves, and all that. Any question before I get into homework number 6 about exams or any other?
I asked this in the chat, but are we still planning to have another quiz?
Yes, so that's I knew that it was this week, but I am going to postpone it until next week. Okay, that will be not on anything materials which is covered today this week. So that way you have time to actually prepare for it. And if you check what was it on, it should be wastewater treatment plants. Anything anything after the so I think it's only going to be the midterms after midterms anything we cover, which will be basically wastewater treatments or anything related to homework number 6. Okay, because everything that is already covered in the midterms will not put that in the quiz because you are already being tested. The things that you are not covered is a um, the wastewater treatment plants. So I want you guys to give some time to read about it. So we will not have this on this Wednesday, but we should have it on Monday. So I'll send more emails about that so that you have information. Again, that will help you prepare for the final. That we know what type of understanding you have. And also, I want you to submit this homework number 6 so that you have some more time. Um, okay, so okay, let me write this one. Quiz next week. That'll be on just wastewater treatment, because everything else before that is covered in midterms. Not testing again, the same thing. Okay, so let's look at the questions in your homework. So the way I organize the slide is to start with something basic mass balance equations, and then I'll show you how you can use the same equations over and over for any types of problems on homework 6 or 7. You'll have only one more homework, which will be on air quality as well as the things that we covered last time on solid waste management. Okay, so mass balance. If you think of mass balance, all the time, you just have to draw the control volume. So let's say this is your system, okay? And we are trying to understand. Mostly, a lot of times you are asked, what's the concentration leaving the systems? Okay, what is the C out? Okay, most of the time, that's the question was, or somewhere or other you'll solve this one to have um, unknown. Solve for unknown. So usually the system is a mixing system or whatever the well mixed system. So this is well mixed. This is assumed, and most of the time that you are looking for now is a steady state. At least the questions are given in homework. These are all steady states because I never ask any questions. What is the concentration after a certain time? There is no time term there. Okay, so you're not asked to calculate a concentration after a time. So that means it's a steady state because time is not a factor. And you have coming in, you have Q in, and you have some kind of reactions. Okay, and reaction could be degradations. Reaction um, could be um, could be settling. Could be anything. So this is the roughly how it looks. Okay, the same Q going out. Um, or whatever the things, if you have different Q, you'll also solve for that one. you might have another system going out Q. So this is your typical system. Okay, so you look for what is coming in and what is going out. And most of the time, the mass balance, if the steady states, so dm by dt is everything coming in, mass coming in, minus uh, mass coming out, plus minus reaction term. Okay, reaction times volume. So I'm going to write it clearly so that you have plus volume time. This is reactions, mass reacted. Okay, inside the system. So and if it is steady state, if it is steady state, usually any mass change in the system would be equal to zero because that means no net change in mass. So dm by dt equal to zero. Okay, so you put this value here, and then you solve for whatever unknown given to you. So let's set up the questions, or at least understand every questions in the homework. So I want you guys to open the homework questions while I am working on any of these problems, so that you should be able to ask any questions on that. So I'm going to open it because I can't share two screens same time. So I'm going to open the homework questions on my side so that I read it while I explain it. Okay, so as I said, the net any homework questions are related to mass balance, so change in mass at certain systems, whether it's a primary or secondary clarifier or aeration tank, whatever is given to you. And concentration, usually there are two type of concentration in the wastewater. Either you are looking for suspended solid, which will be X, okay, or TSS. These are the notation people write. So these are microbial biomass, okay. Or another type of concentration is BOD, which is substrate, S or BOD. So these are all the same thing, okay. Um, so these are the things. Either you are solving for X or you are solving for S. And then you have to also understand how TSS being produced or generated. BOD or TSS, they are removed or they are produced in the aeration tank. So that's where things are, the X, all the biomass is being produced in aeration tank. As the consumption of substrate or BOD decreases, X increases. So they are related by a factor called yield. So this yield is basically amount of biomass created, any kind of biomass created per amount of substrate consumed. Okay, over X over S. Okay, that's the ratio, how much amount of biomass you produce. And then you also know from that chapter, ds over dt is amount of substrate consumed, is basically you have a term that is from the chapter. And same thing, this is a reaction, right? And then also amount of biomass produced is also related to growth. um, and then there is a term for that. Okay, and this term net growth rate, so this is net growth rate g, rg. So this is rg is amount of bacteria produced because of their growing by consumption of substrate of minus the amount they die. So these are all terms, they are everywhere. So you have a reaction term, the flow term, what is coming in and out, then you just plug the value. So let's see if we can solve, at least try to understand the problem. So far, any question?
I have a quick question. I don't know if you can hear me, but I was wondering.
Okay, so let's start with this generic equations. So again, what I wrote here is the mass balance to solve any engineering problem. So the problems I assume is some flow, some kind of flow coming in and the same amount of flow going out. So that's why there is a Q terms given. Okay, so this is the same Q coming in. Okay, and then you have C in, C out, and this is a reaction here, reactions, which is here. Okay, amount of mass reacted is usually the if reaction happen inside the volume, so that's dm reactions by dt, usually volume times concentration changes. Okay, dc reaction by dt, and that dc is the c system inside the system. Okay, and usually if it is complete mixed system, c should be c out, because whatever in the system is what leaving the system, and there is no reaction after it leave the system. So these are just revisiting and this is basically is your decay rates or growth rate or whatever based on what you're looking for. And those reaction terms are this. Okay. And again, it's all steady state. So that means you can put this left side equal to zero. Okay, because there is no change in constant um, net mass of the system in the entire system. Okay. And then you look for what are the flow in and what are the flow outs. Okay, so these are the things you have to identify based on what is asked to you. Also, you have to ask look for what kind of reaction term you have. Is this the substrate or is this the TSS? TSS is X, substrate is S. Hold on.
Professor,
Yes.
Iman had a question in the chat.
Okay. Let me see. Hold on a second. What's going on here? Okay, cool. The question was, so rate of change of X is same as rate of change of S. Um, if not, it's related to yield. Okay, the rate of change of X, because the amount of X produced, because all the amount of substrate is consumed is not everything converted to X. Some of them converted to energy. So that's why that yield is there. Okay, yield is basically what fraction of the amount of substrate become a mass of the bacteria. Okay, so all right, so let's see the example. So that's why I wrote it here. Again, the question one, if I read the question, and you should have this question, a perfectly mixed aeration pond with no recycle or return line, that means this is just one way reaction terms. Now, serves as a biological reactor for a soil community. The pond receives certain volume, so it is given the volume. Then it gives the substrate concentrations or BOD5 that must be reduced to 20 milligram per liter. So that means the S is given. S in and S out is given. It has been found that kinetic constant for the systems are Ks, which is half saturation constant, Ks, Kd was the how fast the BOD decay, and then there is something else. Uh, all those factors are given. There seems like there is a typo here. That's the mu. Okay, that's the mm is written. It's actually should be mu. Mu is the growth rate. Is 1.6 per day. Then Y, which is the yield, is a 60 milligram of volatile suspended solid per milligram of BOD. What that means is that's the yield. Yield means if you produce only 0.6 milligram of suspended solid, which is the microbial biomass, if you consume 1 milligram of BOD5. And then it asks you to calculate different terms like hydraulic retention time, all that stuff. So based on all that, this question is very similar to example number 14 or whatever let me see, the text will, example number 9 on page 330, 322. So, but question is, that example, they solve the mass balance. So I'm going to show you how to solve it. Okay, so microbial, that question was why microbial growth rate is different, So first of all, this is microbial growth rate, which is Rg, R for rate, and G is for growth, which is basically dx over dt. X is the microbial biomass or concentrations. So this is X is again suspended solid, microbial biomass, they're all same, okay, or volatile suspended solid, VSS, TSS, always assume this is X. So what we are saying is dx over dt, which is change in concentration of microbial biomass in the reactor itself, is a first order reactions, which is the rate constant is mu. Okay, that's the growth rate times the concentration at any time. And again, there is a positive sign here because it's increasing. The concentration increase with time. That's why usually you see reaction term, there is a negative sign because things are being removed. But here the microbial biomass is being produced. And it turned out the the microbial growth rate is follows a monode kinetics because it's not really constant. It's also a function of amount of food available. So that's why usually it's a mu max time a food amount time Ks plus S. This is just the notation of monode kinetics. The growth rate is a function of certain maximum amount. So this is something we covered here. Okay. So this is mu, this is S, and basically whatever the mu max, this is mu max, and whatever the 1/2 of that is mu max by 2 is whatever the food required to have this one. This is Ks. Okay, so these are all covered before. So basically the rate of growth just by growth. It doesn't account for the death. Okay, if you account for the death, Rg should be it should be mu x minus amount of this is death rate. Okay, this is death rate, um, which is the net. There is a star. Let me write it clearly. It's growth rate, but with a subscript or the star mark. That means it says that in account for the also the amount of microbial biomass die in the system. Rg dash. Okay, so which is here. So those are the rate constants. If you think of the same thing other way, this is microbial biomass. What about the amount of food consumed? So that's substrate utilization rate, Rs. So Su is substrate. That's ds over dt. Again, this is why I said ds over dt is not equal to dx over dt. But there is a way to connect them. So if you write ds over dt and I multiply dx over, so I multiply dx and also divide dx. So that's how I rearrange it. And it turned out dx over dt or dx over ds is y. The amount of, what it means is the amount of biomass produced per unit amount of substrate consumed. This is the definitions. So you put that value here. So what it means is rate of growth of microbial biomass is same as rate of substrate utilization if the yield equal to 1. That means all the amount of biomass produced is coming from the food that they are created, being consumed. That's not true because they breathe, they produce energy, so there has to be always some percentage, usually 50 or 60 percentage y is given most of the time.
What does the apostrophe RG means? Like
Yes,
what does the apostrophe means again?
again, that's so here this means rate of growth is only growing, they are not dying. That's not true. In nature, some of the bacteria will die. So this growth rate doesn't account for death rate. Okay, so the net growth rate is amount which is growing minus amount is also dying. Okay, so that's a different term. So if you put, so that means Rg apostrophe is the net growth rate is equal to mu m s ks plus s minus kdx. Okay. That's basically death. This is growth. This is net growth. Okay. And same thing, like you have maximum growth rate, you have also maximum substrate utilization rate, that's K. Okay. So K is related to maximum growth rate. It's the same way as the notation of growth rate divided by, because if you think RSU is Rg by Y, the same way it is also that factors. Okay, so these are all kind of given to you. Okay, these are notations, these are definition you should write on your in your cheat sheet so that you know these terms always around, because most of the time you have to solve for volume or something, one unknown term. So once you know what are the unknown, you can solve for it. For instance, here you solve for substrate concentration. That's what we are trying to solve for here in the derivations. And the homework, it asks you what is the theta. So you could do the same thing just by rearranging the equations. You can solve for either. Okay, so let's derive the expression for substrate as example. So again, mass balance equations. You have a reactor, which is basically, this is your reactor. This is coming in and this is coming out. And the reaction is happening inside the system. Okay, so all you know about this and all the reaction terms, I already wrote it here. So if you write this one, let's write the mass balance. Again, it's a steady state. So derive the mass balance equation assuming steady state. So steady state means change in mass d over dt of a system equal to 0, whatever coming in. Okay, so what we are solving here, we are solving for S. So things coming in is this. So Q S0 is coming in. Okay, so this is in. So I'm going to write this one. Let me write even for more basic. Net change equal to all coming in, mine going out. Okay, and this is substrate and specifically reactions. Anything substrate is being reacted inside the system. So that's what you're writing. Because the steady state, it should be 0. Coming in, so look at in the in, that's over here. All these are coming in. So here S0 is coming in. So S0 times Q. Coming out, going out would be, look for in the outs. That's over here on the right side. So Q times S, that's the concentration in the effluent. So S0 Q. Now you have to think of reactions. Okay, so now let's see what's the being reacted. Reaction is usually volume times the reaction rate. Okay, so now how much of the substrate is being consumed or being reacted. Okay, so those are the things we are going to look for it. So think of what is being reacted here is ds over dt inside the system, right? So volume times the reaction term. So which one the reaction that is related to substrate? If you see, there are two reaction terms given here. One is Rg, which is the growth rate of biomass. So that's related to X. Okay, that's the amount of biomass produced. What we are looking for is we are solving for S. S is substrate. So substrate is here, RSU. Okay, so that means volume times the reaction, whatever the reaction is, RSU. Okay, and you don't have to look for the sign issues because that rate constant usually have the sign already there here. Okay. Okay, so now you have the equations. So if you write the entire things, will be S0. If you take Q common, I'm sorry, there is a typo here. Out will be, there is no 0 here. Okay, that's out. So this is S. V times RSU. So RSU is given here. So V, this is minus KS X. Okay, now be 0. So now usually in that equations, most of the time you are asked to solve for the what is in the effluent. So if you are solving for X, let's solve for X. Here the only term with X is this term. So if you take that other side, it's become plus. So X equal to Q S0 minus S. Again, you bring everything in the left side. And if I write this one terms, there will be positive KSV KS plus S. Okay, if I bring everything on the left side. And that means if I solve for x, that will be q h0 minus s. Then this term, if you go other side, it become multiplication ks plus s, and then everything on the numerator here will be denominator. So k, let me write it properly, k. Okay. So now this is one way to solve it for x. But in that examples, if it is probably, if it is asked for x, you can solve for that. If it is asked for retention time, you know that retention time equal to is q over v, right? So if you think of retention time theta, or retention time of water is basically volume over q. So here volume over q. So if I write the same thing here, the q, I'll bring it down here, and that would be S0 minus S. Okay. So again, anytime you have, I would suggest that you practice this thing multiple times. The reason is you just have to look for what is unknown and then you solve for one of that. Usually most of the time it asks for what is the effluent concentrations. And sometimes it also asks for the either the volume of the reactors, or sometimes it asks for the retention time. Okay, so that's just one way. So again, this is just the aeration tank, how to solve for substrate. Let's do the same thing for X, because we solve for substrate. Let's do the same thing for the S. So what I'm going to do is I'm going to write the same thing. Net change in the system would be coming in minus going out plus any kind of reactions. Okay, and we are solving for X term now. Again, it's a steady state, so 0. So whatever things coming in for the X is, this is coming in. Okay, so q x0 minus leaving the system is x, q x. X is concentrations again, concentration times flow rate. Then now I have to look for the reactions. So now here is the reaction. What is being reacted is volume times whatever the reaction rate. And here the net reaction is Rg. So this is the reactions for X. Okay, so and now you just plug the value, now everything is given. And Rg, again, we wrote the Rg value. I'm just going to write it here. Q x0 minus x volume. Rg is basically, we have few minutes ago, this is the Rg value. Okay, so if you write this one, mu max s ks plus s minus k d. Okay, so that's the value for the uh, for the Rg. That's the Rg symbols. Okay, and now if you do this again, you can change to retention time, which is volume over q. So if you put everything back other side, so this will be, or you divide everything by q in both sides, so this will be 0. This will be x0 minus x, and volume over q times whatever this term. Okay, this term, entire term will be coming here. And again, volume over q is if you think that's equal to theta, or the retention time. And in that question, I don't know what is being asked. It asked what is the theta value. Now you just solve for theta. Everything else is given. If you took one term in another side, this will be, theta would be x0 minus x divided by, there is a negative term somewhere, so this is minus and divided by all these factors, mu max s s plus s. So again, any question given to you, you just have to solve the mass balance. Just look for what is asked to you, and whatever asked to you, let's say this is substrate or the solid, suspended solid, just solve for the mass balance for that solid. Then you'll have expressions, and then you should be able to solve for either way. Again, if you ask for retention time, you can solve either way, because retention time is here in these equations. If you, based on what is known, you should be able to calculate.
Do you need an x next to the KD as minus KD?
Let's see, KD time. Oh, you're right. So there is a terms. Yes, you're right. So this is a S term here. Let me, because growth rate, if you see the mass, the rate of dying, let me write it here. And so the rate of dying is KD. So dx over dt, change in rate of biomass is, this is death. Okay, there's a negative term. That's because decreasing because of death. So there is a, thank you. This is a mistake here. KDX. So again, the X term here. So I'm just going to plug the value here. Okay.
Professor,
Yeah.
you also need X on the right next to V, volume, RG. Cause I thought we need X on both of the equation.
I think I have trouble hearing you. Can you say it again?
You also need X on the max equation, max part.
Professor, he's saying that both terms for RG need an X, right?
Yes, let's see. RG. The RG is equal to here. So mu max X. So, okay, you're right. So let me, I put the wrong value here. So this term, yeah, RG equal to this times X. You're right. So this will be X here. So that would be X. Oh, too many mistakes. Thank you. Yes, that X term I missed it here. So this is X here. So that term goes there.
Oh, Professor, at the end, the very last equation, do you have a Q on the numerator, or is that a
No, so Q, so here we change that one, Q over V. So we substitute this equal to theta. So this theta has the Q term. So if you divide Q in both sides, in this equation here, this term, oh, sorry, this is writing the wrong. There is no Q terms because that's the, that terms we already incorporate into the theta term here. So
Oh, okay.
if you divide Q here, that will be 1. V by Q will be theta. So that theta is here.
And so what is it that you have right there next to the X naught minus X? It's in parentheses and you're
Oh, I see. That's just a scribble. There's nothing. I was trying to write. It didn't work out. Okay. So again, this is just expression. I hope this is also correct this side, because just check if I miss any terms. Here it seems like okay. So again, as you see here, this is also theta term here. Okay.
In the last slide, the V is no longer in that equation. Did that cancel out, or was
so that? So again, these questions came twice, so I'm going to write it here. Step. So what I did is this equal to V over Q.
All right. Okay. Thank you.
So that V over Q I changed to theta. That's how I got it. So again, if you know the Q and somebody asks you the volume of the reactor, that's how the V term is there. So again, this is the equation you want to check. Based on whatever unknown, you can solve for it from there on.
What goes into the parentheses next to theta?
Next to theta is okay. Let me write it because I think it's going to whatever the things that's inside this parenthesis before that equations. So if I write it here, so that would be mu max S divided by Ks plus S minus Kd. And let's see the theta x, there is x here. Okay. I'm just putting whatever the equation on the top, I'm just rearranging. Only thing change is volume over Q equal to become theta. Everything else remain the same.
Are we going to use the retention time that we found for the first part A, and then plug it into this equation so we can find X?
Yeah, exactly.
Okay.
No, I'm saying I don't know what is being asked. Okay. So based on what is unknown that's asked to you in that question, you should be able to solve. All I'm trying to say is the solve for the mass balance. So this is important. This term is important up to here, because that's what you have to arrange all the time. And then once you arrange it, you know what is unknown. Okay. And let's solve for another mass balance. So in this case, these are applied to question number 2, 3, 4. Okay, all of them. So I just wrote it here. Let's say you can ask me any particular location. So let's say you can solve for just the aeration tank. Then this is in, this is in, this is out. And you can just solve for the SC. So I'm just going to draw, there are a couple of ways you can solve based on what is unknown. So one of the things you could solve is this is your system. Okay, so this is aeration tank is your one system. Whatever coming in and out from that is what is your going to be. And then another time you can solve for just the secondary clarifier. Okay, so that could be another system. That's my control volume. And if you want to do in another system, okay, let me. This is your entire treatments. Yes, that means there are one coming in, and then there are two leaving. This leaving, this leaving. So you don't have to account for any reaction inside, or the recycling inside the flow rate QR. You don't have to account for that. So let's solve for whichever one you want. That way you know how to solve for this one. For let's say in this particular case, I wrote the equation for secondary clarifier. Let's see how to interpret that. So secondary clarifier is this. Okay, so if I am writing secondary clarifier, let me write it here. Secondary clarifier, you have one coming in and leaving the system, and then you have also, this is secondary clarifier. So what is coming in is QS, that's the flow rate, plus you have a recycle system, QR, that's the flow rate coming in, because this is QS, and then your QR coming in mixed together, and those same things should be leaving the system. So that's flow in. And then what's the flow out? That's QE. What's flow going down is QW plus QR. Okay, that's the flow. If you think of what's the flow in and out, okay, this is again secondary clarifier. And if you think of concentrations, what's coming in, X and S. What's leaving the system, XE. If you're looking for bacteria or suspended solid, if you're looking for substrate, this is S. I think there is a effluent or something, or I have to check what's that. It's usually effluent, and then you have SW, XW, and you can solve for it. It's just basically no reaction here, because the reaction happens inside the aeration tank, nowhere else. So that means everything, you just have to flow time concentration in equal to flow time concentration out. So if you see what's the steady state for the secondary clarifier, so things coming in is, oh, I see what is that. I made a mistake here. So the QS is equal to, what I thought here is, the way they draw this one, I didn't realize. So QS is already accounting for the recycle, because that arrow mark is before. That will be Q plus QR. Okay, so I'm not going to. So this is already accounted for. That flow rate is already accounting for the reaction, the recycled amount. So that's why now if you have this one term, the flow coming in is QS times concentration, which is X, is the concentration of bacteria. And what's leaving the system is 1 and 2. So this is in and there are 2 out. So you just write this one. This is the flow rate going in here or leaving the system, times the concentration is XC. And then what's coming out here is QR recycled times Q waste. That's the flow rate times XW. And then you are solving for whatever the terms not given to you. So if all the flow rates are given, you can solve for that, the unknown concentrations. So based on that, you should be able to calculate. Let's see which equation it is. So this is question number. I think in this question, you are asked to calculate, solve for QS. Okay, how much is the QS? So now how to solve for QS here? Well, QS is, this is the term given here. So if you write this one, it will be, let's see, XW, let's see, XC value is, a lot of times you can say XC, the amount of bacteria usually leaving the system or in the treated wastewater is nearly 0. That's a lot of times you can, if you see the actual textbook, that's why, because you don't want bacteria in the effluent. So a lot of times you assume that they are very, very small compared to everything else. So you can also almost assume this equal to 0. So if you do that one, and then you have to, before you solve this one, I'm going to write all the assumption. And then next one is you can solve for QR, is because usually QR is not given. So QR is basically, if you think of QR, the flow rate going out here. So QR here should be, if you write what is the QR, so this should be, QS should be, another way to write is, I'm going to write just the flow mass balance. So whatever flow coming in should be whatever flow going out. So that will be QE plus QW plus QR, right? So that's, QS is all coming in, this is going out. So if you write QR, there will be QS minus QE plus minus Q. So if you have those value QR, you put this value here, X equal to 0 here, this term becomes 0, and then QR, you plug this value, you should be able to get this answer. So let me write this one. QSX would be QR equal to QS minus QE minus QW. That's QR. Then you have a QW here time XW. Okay.
Should we be solving for Q? Oh, never mind. I see. Never mind.
Okay. So that way QW cancel. So you got this, then this value would be QSW, or let me see, QX, X should be QS times XW. I'm just multiplying, taking the QW inside, QE XW. Now you are solving for QS.
No, or that should be QR, right?
I substitute QR equal to this value here. This QR, I substitute this.
Yeah, but in that equation where you did the mass or the volume flow rate,
Yeah.
didn't you solve for Q? Oh, I see what you did. Okay, you just plugged it in there.
Yeah,
Got it.
so I'm just solving for QS because that's the one. I think that's the one your homework solution. They ask for that QS. Because
Got
if you
it.
know the QS, you know the hydraulic retention time. Because if you know the total amount of flow coming in, you know the hydraulic retention time. So it's volume over QS. So hydraulic detention time in any system is the volume of the system divided by flow in the system. The flow in the system coming in is QS. So if you solve for QS, you know the hydraulic retention time. Because I think what's that asks is, what is the hydraulic retention time in the aeration chamber? So that's the volume of aeration chamber divided by whatever the flow coming into the aeration chamber, which is QS. So if you solve for QS, you should be able to solve for theta. So again, QS would be, if you take this one, so this will be, let's see, I'm just going to write it here, just rearranging the equations. It will be by XW minus X. I think that's the value. So if you know the QS, then you know how to solve for the hydraulic retention time. So again, any question asked to you, you just have to just do the mass balance and see what is unknown, solve for that. You should be able to get those answers. There are only 2 or 3 systems. Either you can do for aeration tank or you can do for settling tank. In fact, your settling tank equations, that's the question number, let me see. This was the question number 3, 4, 5, okay, 3, 4. So in question number 3 and 4, you are asked to calculate the settling velocity. So that is basically solving for this. In the secondary clarifier, so what's coming in is here. The flow rate that coming in is Qx equal to Q plus R, Q plus R. So Qs is coming here, and then X equal to Qxc. Okay, let's write this equation. Don't worry about this one. Let's write these equations. Okay, so one of the question was calculating the settling velocity in secondary clarifier. Secondary clarifier, if you do the mass balance, what you should get? Let's write it here together. Only you have to look for is, this is your control volume, whatever coming in. So this is in, this is one out one, and this is also out two. Okay, so if I write secondary clarifier, this is going in. Okay, so this is QS X, and this is QE XE SC, and then this is going to be whatever things, because it doesn't really say that there is a flow, all that stuff, but let's write that one. Okay, um, if you see what's coming in here inside the system, there is a flow coming out or not. Just by looking at that one, what you see is there are amount of bacteria coming into the secondary clarifier, and then some of them are settled and rest of them leaving the systems in the effluent. So the mass balance would be whatever coming in minus whatever coming out should be the amount settled. Okay, that's all you are saying. Whatever settled is actually moving out of the system as a flow here. So the mass balance of the settling tank would be mass in should be mass out, rate of mass out, minus plus mass settled. Okay. So let's write whatever mass coming in. So this is QS times, again, you are solving for the microbial biomass, X. Okay, X is the microbial biomass. And what's leaving the system is QE XE plus amount of particles settled. Okay, so the amount of particles settled is basically concentrations, whatever the concentration in secondary clarifier, concentrations times volume. Okay, rate of change of concentration over time, like this. So there is a time term here. So I'm just writing this one, QE XE. So what's the concentration settling is whatever the concentration in the secondary clarifier, and whatever concentration in secondary clarifier is whatever coming in. So that's X, that's coming in, and the volume is how much volume settle is basically area times whatever the settling, the whatever the particle move is the what particle settle. So let's say it moves g directions, certain dg over dt, so let me write this one. Dg over dt means the velocity, how fast it is moving, because that's the one settle out of that control volume. So this will be basically, I'm just writing here, q e x c. So this would be concentrations coming in times surface, the area of the secondary clarifier times the settling velocity. Okay, so if you write this another way, you should be able to solve for settling velocity. I know that in TA also asked me this question, is um, why we don't use the overflow rate. So let's think of the differences. Okay, so this is one way to solve mass balance equations. What overflow rate does, it's basically overflow rate is velocity of settling. When you do this one, this velocity of settling is a function of, basically there is a d terms here. Okay, it's related to size of particles. So when you know exactly what's the size of particles, you know exactly what's the settling velocity. But here I don't give you what size it is. So I mean, you could write that to solve for velocity of settling, but it's only remove the particle with a certain size. So it doesn't remove everything, because it means that if your overflow rate is same as settling velocity of a particles, you know the diameter of the particles. Okay, so this is not, it means that you can use this equation to solve for the minimum size or the maximum or minimum size of particle that can be removed. Okay, after minimum or bigger than that size will be removed. This is what you use to solve for the particles. Okay, but if you use this equation, you should be able to solve for, you don't have to even think of any size of the particles. It just says that how much particles settle. There
Are
are,
we assuming that there's no reaction going on in the clarifier?
well, this is a reaction to some extent, because the reaction here is the removal because of settling. So this term is kind of a reactions. But this is a reaction means, things removed by certain mean, so this reaction is settling. Particles are moving in, let's say you take a small portion in the liquid, so if you think of a bucket and you look at just one small section of liquid, whatever coming in, whatever coming out, minus whatever the leaving the system because of settling. So this is leaving the system because of settling. So that particular question, that this question keep coming in the question number, I think question 3A and 3B, both of them you should be able to solve by using these equations. No, question 3A and 4A. And the last one is this, okay? A lot of times you are also asked to calculate the mass balance for the entire system, okay? Entire system, or it could be just the entire treatment. So for instance, here, I'm going to make it a lot easier to, because this the way the picture is drawn might be confusing to some of you. So I'm just going to make it easier. So you have a primary treatment unit. So primary clarifier, okay? Then you have secondary treatments, okay? Primary treatments, so then you have secondary treatments. Secondary treatments is aeration tank plus the settling, okay? So the combination of that. And then this goes to river, okay? And whatever coming settled from the primary and secondary clarifier is become like a waste or waste. This is waste, okay? Or the sludge leaving the system. So now I asked to do the mass balance for the entire system. So my control volume, if I do control volume, so this will be, let me do control volume. So this is the control. That means you have one going in here, one going to the river, and one goes to the the sludge as a sludge. So if you do mass balance for mass coming in, so this is TSS in, okay, and this is Q. This is QE. This is TSSE. So think of this as a S in, SE, because TSS you could write. Oh, I'm sorry. This is TSS is suspended solid, so it's not S. This is X. So this will be X in or XE. Okay, the same notation. Here, just change the notations. And then this is the reactions. So now when you do mass balance, so this is everything coming in, should be everything going out plus whatever the reaction happen inside this entire control volume. So that's what this is written. So if I write the mass balance equation, I'm just not going to write it here. Just let's write what you learned from before. Again, steady states equal to 0. Whatever coming in minus whatever coming out plus any kind of reactions. And there is a reaction here because this you are solving for TSS or microbial biomass. Microbial biomass is produced in secondary treatment plants because that's where the BOD is being consumed. So you have to account for that reaction there. So let's write this one. 0 in, whatever coming in is Q times TSS in. So that will be XIN minus what's leaving the system is QE times XE. There is not just one out, there is another out here, which is the sludge that going leaving the system. So that will be minus M dot That's already amount of mass leaving the system m per time. And let's write the reactions. So now reaction means how much biomass is produced in the secondary treatments, or because that's the only place this is being produced. In our primary, they don't produce anything. Secondary, that's where the biomass is produced. So biomass produced is basically would be, let's write this one. So that would be the concentration produced here. So that would be how much. The one way to write this one is I'm going to put it here. So let's say how to explain this one. The biomass produced here is, let's say this is the biomass produced. That's what we are getting, try to get at, okay? If we know this one, we can multiply that times Q, whatever the Q, X produced. Okay, now our goal is just to find how much X produced, okay, how much biomass is produced. Well, we don't know how much biomass is produced, but we know how much BOD is consumed. How much BOD is consumed is exactly how much biomass is produced with a relations to with Y. So X produced divided by BOD consumed. Okay, so that's the, because that's the ratio is equal to Y. Okay, the yield is basically BOD consumed. BOD consumed, or so that ratio is Y. So that means you can write here X produced would be Y times BOD consumed, means whatever coming in minus whatever going in the system. So that would be BOD in minus BOD out. So if you plug this value X equal to here, you should be able to solve for the M dot, because BOD is given there to you. Let's see, what's the equation give? Without the size, would you have fraction settled right? Yes, without the size, if you don't know the size, you can calculate Vs over V0. But again, those are, that V velocity of settling is related to, if you use the previous equations, that's based on the size. So that what it says, that if you know the particular size, the fraction remove would be, you will be able to calculate. Is activated sludge tank the same as aeration tank? Yes. Or does activated sludge tank include aeration tank plus SC plus RS? Okay, so the secondary treatments is included everything. It included the aeration tank plus the secondary clarifier, and also the yeah, those two, and including the recycling, RAS, return activated sludge. Yes, you're right. The settling velocity we calculate then, is that the average? Yeah, this is average. All the settling velocity you calculate average, because you don't know the particle size. This is just the distributions, because based on particle size, there is a settling velocity for different particles. So the mean value is what is you are calculating based on this mass balance.
Professor,
Yes.
I had a question on that yield relationship.
Okay.
So that's the one you wrote down there is just kind of like a general equation, kind of for all of them, and it doesn't necessarily correlate with the BOD in and BOD out way that's on the figure right there, right? Because you got the BOD in, BOD out from the primary treatment. So for this one, would like in this case, would BOD in would BOD in, but would BOD out be
so BOD in and out of secondary treatment. So this is what, when I write X produce is only produced in the secondary treatment plants, right? And that's
Okay.
only the aeration tank. So this related to only aeration tank, because that's the only place is being produced, not in the clarifier, not in the. So if you know the aeration tank is given, or even the secondary treatment, you should be able to, which is given here, the BOD out. So this will be, Okay, the way I wrote this one, maybe the notation is here. So this will be BOD out based on this particular equation, because I wrote it here wrong way, because the notation in the picture is different than what I wrote. I wrote generic equations. So here the basically whatever the coming in, so this is BOD out is coming in the secondary treatment system, minus what's remaining is BODE. So that difference is what is being consumed. For if you look at the picture here, that's the right hand, that's the notations. Okay, so the last one, which is also example 5, that's maybe it's not part of the homework, but this is just want to say that you can also do overall mass balance for the entire system. If you do the mass balance for the entire system here, this is the control volume, you should be able to do that. So one way to do is, if you think of here, let's say, if you do whatever happened inside the aeration tank, so this is for aeration tank, what is saying is amount of this is amount of bacteria produced inside aeration tank is the same as amount of substrate consumed with a relationship with yield. So this is something we already covered. This is what we write here. This one is the same as here. Okay, amount of produced times the rate at which produced is the same as the rate at which BOD consumed with a function of yield. And this one is the mass balance for the entire system. So if you see, this is the, let's see, overall system. If you see what's the leaving the system, let's see what it is. I think this is the for aeration tank, not the entire system. This is for mass balance for aeration tank. I'm sorry, this is for aeration tank, so not for the entire system. So I'm going to erase that. What I'm doing is I'm just calculating whatever happening inside this one, and I wrote the mass balance equations. So if you look at the example 5 in the handouts I sent you, this is the mass balance that's done. So that's all for any kind of wastewater treatment plants examples or questions. So I solve for any mass balance for whether it's a aeration tank or secondary clarifier. Just look at them again and see which one you don't understand. And you can ask, now you should be able to solve any questions on wastewater. At least you should be able to solve the homework question related to mass balance.
Professor, on the last equation, did you say that's for the entire system or just for the
Aeration tank. So I didn't read the title. So this is for only aeration tank.
Okay. Thank you.
Okay, so any other question related to homework while I am here before you go to the air quality? So
you go back to where you talked about the settling velocity. I had a question on that.
Okay.
No, back one more slide.
Okay.
Yeah, this one. Shouldn't the X next to the AV, shouldn't that be XE?
Which one?
So the last part that says XAV settling, shouldn't
Yes.
that X be XE?
So let's think of what's happening here. No, that's not true. The reason is you are not. Let me think. It's conceptually what that means. Let's see. X in or X out. Amount of particle that's the system. It's yeah. Whatever reaction happens, it should be in the system. You're right. So that should be. I'm sorry, you're right. So this should be XE because whatever happening here is what's leaving the system.
Okay, thank you.
mistakes. Yeah, so for any reaction, complete mixed system, if a reactor effluents S out should be S equal to S out. If it's a complete mix, because whatever the in the system is what leaving the system. Okay, I think, I saw that, let me see the campus wire question just in case we have any other that we didn't answer. Any other question related to those, the TS should be able to answer. I thought I'll be able to. So there are questions related to DO. Those are on in those other classes. There are questions related to, again, that equations is just we derived. So that should be okay. Then there is another question related to DO mix. Again, the same thing. DO is you already did before. So that's nothing with getting the correct answer for B. So I checked all the answers I checked. These are all correct answers, whatever is given there. So if you're not getting that right, what you can do is you can send the screenshot of your questions or answers privately to me or the TAs. And then we'll be able to show exactly where you might have difficulties. Or question number 4B, can you explain 4B? Okay, let's see. What is question 4B? The suspended solid entering the plants are mostly composed of organic materials with the chemical composition of certain materials. The solid have potential to consume oxygen. So you have a chemical reaction for B. So let me write it here. I'm going to write it here, okay, for B. So that reaction is given C5H12 plus 3O2 plus NH3 goes to C5NS7 NO2 plus 4H2O. So basically, this is your BOD, okay, and this is your DO demand or BOD demand. This is the substrate. I'm sorry, this is the substrate, and this is BOD. That means you need 3 moles of oxygen to consume 1 mole of that particular chemicals. So consider the removal of BOD from the COs by settling of organic particles in the primary treatment unit. Determine the biological oxygen demand in of the flow entering the primary unit. Okay, so you are asked to calculate BOD coming in. Okay, so let's see. So how much? So BOD in, you are asked what is the BOD in. Let's think of what is BOD in. BOD in must be what is in the let's see, did I give you the symbols of that? Okay. The primary and the secondary. Okay, so the primary, so I'm talking about the 4B, so I'm just going to draw it here, that way everybody understand, because I didn't say this slide. So this is primary. You have things coming in, BOD in, and then you have something leaving the system, that's S0, which is BOD out, okay? So we ask what is the BOD in. So your BOD in must be whatever the leaving the system plus, because your BOD is also being settled, and whatever the BOD is removed in the primary. So delta BOD removed in primary. So whatever coming in, some of them are removed in the primary and plus some of the things leave the system. So this BOD removed in the primary is what? Is related to suspended particles. Um, this, then if you know this term, then you should be able to calculate. So delta BOD removed in that primary treatment unit is basically the way the BOD is removed is based on the reaction that can happen in that oxygen demand. So some fraction of the BOD is removed in the primary because of these reactions. So that's what it says. So what are the reactions is, let's see. So you have this reaction, you have 3 moles of oxygen is required for 1 mole of C5H12. If you know the molecular weight, so this is 3 times 16, 32. 2 oxygen is 32. So that means 32 gram of per liters of oxygen that's the amount of BOD demand is equivalent to 1 mole of this. So C5 is 12 times 5 plus 12 times 1. So 12.60 plus 12, 72. So what you are saying is your 72 gram of um, the particulates that is removed by settling or degradations is consuming this much of 32.3 BOD, 32.3 milligrams or grams of oxygen. So I'm going to write the formula here. That way you can look for this one. So whatever the particle the amount of BOD is basically oxygen divided ratio of whatever the substrate ratio. So that C5H12. This one is 36. No, 32 times 3 is equal to, and this is TSS. Let me write this one. Then we can explain. So the amount of BOD is removed in the system is the same as whatever the particles settled, that concentration in the system, times the ratio of oxygen divided by the particles consumption of that. Because this ratio is, let me see, the reason I'm trying to, it need a little bit more, I'm confusing yourself because I think it needs a little bit more explanations. I was thinking whether we have time for that. How about we do this one? I will write this one, how to explain it in the campusware so that you have more understanding of that, because I'm going to, that multiple step how to come to these equations. Because we have only a few minutes. I'd rather write it on campusware, that we don't want to solve this one for the entire homework now. But just this is the formula and I'm going to explain that one. That's for Laurel who asked these questions. Let me see. Kiko says x equal to x without CSTR assumptions. X equal to x without CSTR. No, that's not true. So the x is the amount of particulates, right? So the suspended solid. In second, I'll clarify, remove most of them. X is very small. In fact, x is very high. X is not equal to xe. They are removed by sedimentations. Let me see anything else.
Professor, it says oxygen concentration, and then it says is that an arrow or like?
No, that's that oxygen concentrations, not arrow. So this is the total amount of oxygen based on the stoichiometry. So 32 times, let me see. So this one would be 32 times 3 is 70, let's see, 339, 90, 96, so 96 gram. This one is based on stoichiometry, 72 gram.
Oh, okay.
Okay, based on the stoichiometry. So that's the ratio. So if you know the ratio, that means if every 72 gram of the organic carbon or substrate is removed or being there, is consuming 96 gram of oxygen. And 96 gram is BOD, biological oxygen demand. And so if you know how much of TSS is removed in that primary, you know already how much BOD is being removed out of the system. So this TSS is removed in the system in the primary. So this is TSS removed in primary. Or this TSS is basically organic, whatever the organic was removed. That's what they are saying. Okay, so I think we spend most of the today class about homework, which is fine. I'm okay with that one. That means I have to record some of the air quality if we don't finish it. But I guess, it is a time well spent. The reason is I rather have you do the homework well, and because that's and understand it, because that's part of the final. Also, that's part of the I will not ask question on quiz on equation for sure. I will ask question on concept only. So you should know the concept, like, what happens in the activated sludge process is basically you supply oxygen and that produce the biomass, and the BOD is being consumed. What happens is secondary clarifier. That's basically settling all the bacteria, and then some of them is recycled. So those concepts are important to answer questions, and that will tell you, why the some concentration decrease, what some concentration increase. So I think, that's all for the homeworks or wastewater treatment plant related questions. And also I wanted to cover a little bit of mass balance. The reason is you are going to use the same mass balance for solving air quality. There is no new concept. You are basically looking at the flow in, flow out, and putting the reaction term. So that's why it's very important for me to revisit again for any mass balance reactions, because in the final you will have schematic will be given, flow in, flow out given, concentration are given. You'll have just one unknown, and so you just have to write those and solve for it. You're not differential equation. These are not derivative or integration. So it should not. It's just basically rearranging the equations. So that's why it's very important for you to understand or revisit the concept of mass balance. Okay, so I have 10 more minutes, uh, 10 more minutes of time remaining. So what I'm going to do is, instead of trying to rush through everything, I'll just, we can do either a question answer session, or we could just tell you what we are going to cover in air pollutions in the next class. If you have any questions on homework or anything, we can answer that. It's concept, not necessarily solving it, because that will take longer. If not, what I'll do is, let's do this way. We have another office hour, so that means you should be able to ask that time. Think of air quality, why even we need to learn this one. And I encourage you to watch this video, these 3 videos I said particularly here, because these are related to LA. The first video is about, do you know that 7 of the 10 most polluted US city for air quality belong to one state? And obviously, if you think of what that state would be, you will be not surprised. It's California, and then particularly LA is notorious for air quality. And if you think why it is that, most of the time people think it's probably we're doing something wrong. It's not. It's just we have lots of car, and then somebody can ask, well, there are a lot of car everywhere else too. Well, you don't spend that much time on the traffic. If you think of how the car works, if your engine is ideal, that's the time where the combustion is not efficient. So that means if you are driving a car at 60 miles per hour, you are producing less pollutions compared to if you are staying in the traffic, slowly moving and going, because that's the time engine is really working, but it's not efficient because you don't need to move. So this incomplete combustions is actually producing all these shoots and all um, these pollutants. But the complete combustions is always going to be carbon dioxide. So carbon dioxide is not the main pollution here. The main pollution is smog, nitrogen oxides, small particles, all the other factors. So we'll learn about those concepts. And then also wildfire. Every time we have a wildfire, you see these issues, air quality become worse. So I think what I encourage you to do is read the chapters. I share this one. It has very interesting chapter. The reason is lots of text, but those texts are useful for you to improve your understanding. Here, I'm not going to go details about it, but I'm just going to explain that most of the time when you are thinking of pollutions, you are looking for this. You might look for this NOx. What does that mean? NOx means nitrogen oxide. It could be NO, it could be NO2, it could be all these different types of this X means 1, 2, all these different numbers. Okay, but usually the most common one is NO and NO2, nitrogen dioxide. And so these are being produced. The reason why it is produced is because if you think how the engine works, if you burn something, you are not actually burning carbon, not you are not burning nitrogen, but you are burning with oxygen. But our atmosphere is 73 per 78% nitrogen. So when you're so basically your gasoline or whatever things are burning in the engine, and then the air is moving in because that you need oxygen to burn it, and that oxygen, your atmosphere air has only 20% oxygen, or roughly that much, but 78% is nitrogen. So that nitrogen is every one oxygen you have like 4 nitrogen going in, and so those nitrogen is also going to be born with react with oxygen. So that's how the nitrogen, when they react, it becomes NO2. That's because your atmosphere has so much nitrogen. So any combustion produce that. Any combustion also produce sulfur dioxide, because sulfur is also part of many organic carbon. If you think of our body, those are also micronutrients. So every gasoline has some amount of sulfur. And then there are other sources. So instead of just producing carbon dioxide, you also produce this NO2, SO2. And they are more potent than carbon dioxide when it comes to acidity, because they go to atmosphere, they dissolve, they produce NOx, produce nitric acid, sulfur dioxide produce sulfuric acid. That's how acid rain come in. Okay, and then you also produce carbon monoxide if it is in complete combustions. And the carbon monoxide particularly is very poisonous. That's why you see in your home, inside your home, you have this carbon monoxide alarm. The reason is, you breathe in carbon dioxide is not as harmful as carbon monoxide. The reason is it's a smaller compound compared to carbon dioxide, because it has one oxygen, and so it confuses our blood cell with oxygen. So that means if you have lots of carbon monoxide we are inhaling oxygen and carbon monoxide. This carbon monoxide is much more reactive towards your hemoglobin. So that means your hemoglobin is no longer bind with the oxygen. It will bind with carbon monoxide. So that's why you see lots of movies. You see the either the villains or the sometimes you see the people are inside the car and they put the exhaust fan back inside, and that's how people suffocate and die without even having a pain. So a lot of times that's why we have the air monitor, quality monitor in your home, because carbon monoxide is not painful. So even you are inhaling carbon monoxide, you will not know it. It's just you'll um, if you are sleeping, you just sleep, and then your oxygen level will decrease to a critical level. Then people die like that. So it's very important to monitor carbon monoxide. So that's why I say that read that textbook. Textbook has all these explanations. Obviously, I'm not going to ask questions on those concept or the understanding, but this is important for you to learn, because there is no other time you can learn about those unless you are working on this field. So that's why I say read that. I share the textbook, read it for your own understanding. What we'll cover in this class is conceptual solving problem. I'm not going to go through details about why carbon monoxide is bad, worse than other. I just explained one example. Same thing, you can think of every single thing written in these slides. You have some story behind it. How ozone is being formed. Ozone is obviously all the time you think O3 is produced at the very upper atmosphere that protect us from UV light. But ozone is also very reactive. So if you have lots of ozone in the ground level, those are toxic to us. So we don't want the ozone to on the ground level. We want ozone to be upper atmosphere. But ozone is being produced in the environment, the ground level, because of this reaction with other chemicals, the particular these volatile organic compounds that's being produced from smog and all that. They react with the atmosphere, and that's how when they react with the oxygen, the ozone is produced. And if you have lots of ground level ozone, that will cause cancer. So you got to understand what caused that ozone level. Think of radon. If you're living in Culver City, lots of pollutions because of radon. That's a natural radioactive emissions. So what it does, how it is being produced. And then you have particulates. Particulates are basically when you drive the car, the car tire is being friction with the roads, and that's how it produces particulates. And the lead is mostly coming from gasoline, because before the lead was used in the gasoline to make the engine more efficient. Now there is only lead. If you see most of the time, if you go to any gasoline station, it says only lead. Means there is no lead. The reason is obviously lead is extremely toxic to us. And once they found out, 1970s, they banned lead in gasoline. But still the remaining amount leave behind in the environment. But lead is also used for a lot of paintings or paint. So if you have any kind of paint in old building, those leads are there in the as a paint. So these keep coming back to the environment. So as I said, these for each pollutant, we have a story behind it, and that textbook has the story. I really encourage you to read that because I can't really cover those talking about the story. So I wrote it here so that you can see those. Again, just look at those questions, particulates. Please read those textbooks so that I don't have to go through all this. And so what I'm going to do is next class, I'm going to focus a little bit of health, because I know this is something personal to many of you or us. Um, you want to know how the particulates get into lungs and what it does. So I just put some materials here so that you know what it affects. If it's carbon monoxide, it's a cardiovascular disease. If it's ozone, it's a respiratory because it produced reaction, because it's the air, it produced the inhalation issues. So all these other things are written here. These are all present in air. It can affect our different organ. For instance, carbon tetrachlorides, that's the organic, that's like a solvent is used in previous, in the refrigerators. Old refrigerators being used. That every time you turn on the refrigerator, that some carbon tetrachloride leaks to the atmosphere, and that can also cause liver disease. So these are all different things, as you can see. These are all very important things. I don't want you to miss any of this. So please read the textbook. One of the important thing you remember during the wildfire times, the UCLA sent out email talking about how the air quality is bad, and they write air quality index. So you might wonder, what is that air quality index? Well, air quality index is all about looking at these 5 different compounds. Number 1 is ground level ozone. Number 2 is particulates or the suspended materials, carbon monoxide, sulfur dioxide, nitrogen oxide. So these are the 5 things they look for: ozone, particulates, carbon dioxide, sulfur dioxide, nitrogen oxide. So they combine them together, because people, if you tell them this each concentration is different, they don't understand what they mean. They combine them together and come up with a one number. So that's one they write from 0 to 500. And so in LA during wildfire times, if you are in westwood areas, you'll get something like 150 to 200, and that's unhealthy. So it unhealthy means they say that you don't walk outside. And then if it is go to beyond 250, or which is very near to wildfire area, You really have to have mask. You can't really, you'll feel it in your lung. And above 300 is pretty hazardous. And if you think of city like Delhi, particularly, China used to be pretty bad, but now India, big cities are pretty worse. So that's particularly Delhi. The pollution level is always in winter time, particularly now, is more than 400 or 500, even that bad. Can't see even in midday the sun. So as you see, these are all important issues. And so those are all discussed in the book. I really suggest that you should read that, because there is no way for me to explain about all these texts in this class. That's why I wrote all these YouTube link, particularly here. What happens to the if your particle get into the lung. So watch this video. I put it there so that you can watch later. And so what we are going to cover next class is the clean air what. So these are I wrote these things, but most importantly, this is what we are going to do. We are going to solve mass balance problem. So if you see here, this is your home and you want to know how much radon emissions happen inside the system, is change in concentration of radon in your home. Volume of air inside your home is V, or that's internal volume, is whatever the radon coming in, Q times Ca, that's the coming in. And then whatever leaving the system, Q times C, and whatever reaction inside happen. One is the emissions, that's because your ground level is polluted, that's how the emission happen. So that's emission minus whatever the reaction happen inside the air, because whatever radon, it will also react with atmospheric particulates and all that stuff and degrade. So this is a source, and this is a sink, and this is in, this is out. And again, we are not going to solve it. I'm going to give you directly the solutions. So unlike any whatever the wastewater treatment plants we solve, air quality problems are unsteady, because usually the source is not continuous. If it is steady state, I will tell you. But most of the time, I ask you to determine the concentration at a certain time. So these are given to you, the concentrations. That's why you see CT means is a function of time. It changes with time. So any air quality problem, next class, I will set up the mass balance and I'll give you the equation. You just have to plug the value and get these answers. So the important here is to understand different concept. So we'll solve next class both indoor air quality as well as outdoor air quality. Means if you have a big stack of flume coming out near an industry, you want to know how far this plume will migrate and what concentration you will experience if you are standing on the ground. So those two are the quantitative problem we'll solve next class. But this class is not about only that. This class is a lot more about also understanding air quality and all that. So I will highlight some of them, but I will not explain everything. And it's very important for your understanding. You should understand all those factors. What is PM 2.5? Means every particle less than 2.5 micron. What is PM 10? Every particle less than 10 micron. So you should know that concept. What is ozone? What is lead? All that factor you should be able to understand if you read the textbook. So again, please read the textbook. Next class we'll solve those concepts. I'm not going to go through those understanding of what is carbon monoxide and all that health aspect. I'll just directly solve engineering aspect of it. All right, so that's all about the class today. Next class is all about air quality and solving the problems, and everything else will be your reading. And I'll put some quiz questions. The quiz question in the sense for just so that you know whether you know those material or not. I'm not going to ask similar question on final or anywhere else. It just I put it so that you know these are the things you can read from the textbook. These are all interesting. I really like the air quality chapter because a lot of things are on the health side. So read those. All right, so that's all the class today. Any questions?
I had a question about the office hours of the TAs. They're gonna be the same this week, right? Like the as the ones they have in CCLE,
Uh,
or
I
did they like added like more hours, or just
They added more hour because I asked them for the homework. I said that can you have more office hour, at least particularly today, tomorrow. Um, um, at least for those whose office hour is after Wednesday, they will have it now, so that they will help you in answering any question related to homework. Because I understand that, because I myself didn't work during the Thanksgiving, so I was not expecting that you will be working. But I know a lot of you did work and ask questions. I felt guilty that I didn't really respond.
okay? Thank you.
Okay. All right. See you next class. We'll have again air quality problems. We'll solve questions related to concentrations in air. It's one long question in your final. Okay. So that's why it's very important for you to understand how we set the mass balance, how do you solve it. But so you have three questions in the final. One is a wastewater treatment long questions. One is a basic mass balance questions, just like, like a river, wastewater, or whatever things, coming together. And one is air quality. Okay. And then everything else. So these two homework will be your final, most of them. So homework 6, I cannot emphasize how important it is. Should learn how to do it well. Okay. And I hope this review was helpful, because I think this will keep coming for almost every questions in related to homework. And I solve any question that's possible related to homework number 6. And I also share the solutions on the solutions of 5 questions by email. You should have them. It should help you. We'll still have office hour on Tuesday, even though I kind of cover everything what I need to cover that day. But just that day, you can ask any questions, not just here about homework, but also other things that you are concerned about. Maybe we can also cover, I can share the solutions of the midterms during office hours. That way, if you have any question on that. All right, see you on Wednesday.